Next talk is by Arman Ismaili from Rio de Janeiro, who is going to talk about new physics at Icecube.
Thanks. So, it's my second talk, this part on the neutrino. So, I'm going to talk again about the Icecube, but this time I will focus on the atmospheric neutrinos. Part of it I assume for the students, I assume that you know what is the atmospheric neutrinos and how they produce and all this stuff. If not, Esteban will tell you in the next lecture, I think. Yeah? So these are based on the things that I'm showing to you is based on several papers in collaboration with Alexei, Smirnov, Orlando, Francis Halzen, Pedro de Holanda, and the friends in Unicamp generally. But let's see how much I can cover. So I showed you this plot in my last talk, if you remember, that I was talking about these astrophysical neutrinos and neutrinos that are coming from the GZK mechanism. But at that time, if you remember, I told that the atmospheric neutrinos are the main problem in the Icecube neutrino because you have to reject a huge background. But now you can think that, well, you can look at the Icecube as an atmospheric neutrino experiment. So you have a lot of events, is basically the biggest, the largest atmospheric neutrino experiment. So we can measure them and start to do neutrino physics, oscillation physics. So let's see what we can learn in this sense. I'm not going to repeat the Icecube description because I already gave you, and for the other experts, they already know. So just very quickly, is in the South Pole, you have two kinds of events, muon tracks and cascades. You remember I told you the advantage and disadvantage of each of them, that you have a better energy resolution for the cascades and you have a better angular resolution for the muon tracks. And those are these are the main 2 points. So actually, Icecube already published several papers on the measurement of this background for the astrophysical neutrinos, which is atmospheric neutrinos. The first one actually comes even for the time that the Icecube was not complete. It was like the half of the Icecube. It was 40 strings out of the 86. Because they implement the strings every summer, the strings. So during one summer to the next summer in the South Pole, the detector is there and collects the data, even not the complete one. So the first one they published in 2011, it was with half of the Icecube, IC40. It was the energy range from 100 GeV to 400 TeV. This is the first time that we have data at this range, TeV range, for the atmospheric neutrinos. And you can see this was the configuration of the strings, and this was the data that Icecube measured, the points with respect to the zenith angle, events per beam. And this is the prediction, more or less, very good fit you can find. And of course, Icecube continued to take data. Later, they published another paper for the atmospheric neutrino oscillation. This time they measured by the muon tracks, they measured from 20 GeV to 10 TeV. They divided the data set to 2 sets, low energy part and high energy part. And in the low energy part, you have the oscillation, and in the high energy part, basically, you don't have oscillation. I will tell you later. So this is another data set. You do the analysis in terms of the sin square and the term square. This is the result that the Icecube got at that result at that year, 2013. 2014, they updated. 2018, I think this is the last publication of the Icecube. And you can see that now Icecube is getting a result more or less as even better than SuperCamuCande, more or less like the T2K and the others. So it's really atmospheric neutrino experiment in this sense. Not only by the muon tracks, but also Icecube measured the atmospheric neutrinos through the cascades. And this is very important because this is the first time that we are seeing the atmospheric new efflux. We don't have any measurement of this besides the Icecube data. And this is again, this was done by the Icecube 79. I think they didn't update this analysis later, as far as I know. So this was from the 80 GeV to the 6 TeV. Here you can see, and they have seen something like 1,000 events that more or less half of them is background, but half of them can be is coming from the new flux. So, but what is the oscillation of the atmospheric neutrinos? And how we can use these atmospheric neutrinos to search for new physics, basically. there is one main point, and the main point is that if you look at the if you think about the nu E, nu mu, nu tau, the three types of oscillation that can happen between nu E and nu mu, nu tau, two types, or between the nu mu and nu tau, the oscillations that can exist. The oscillation of the nu E in the high energy is suppressed because of the matter effect. In fact, the oscillation length is equal to the diameter of the Earth. But because there is a matter effect, so when the energy goes up, the effective mixing angle will go to 0, so there will be no oscillation for the nu E in the high energy. For the nu mu, nu tau is the opposite. There is no matter effect for them, so there is no suppression due to the matter effect. But the oscillation length will grow up and will be much larger than the diameter of the Earth, so there will be no oscillation again for the nu mu and nu tau. So the final message is that if you go to more than 100 GeV, there is no standard oscillation for the neutrinos, atmospheric neutrinos. And that's a good news because it means that we can use these more than 100 GeV, which is already measured by the Icecube, we can use this data to search for any new physics. Because if you see any oscillation, that's a new physics. And that's a very clean way of the new physics. Of course, you can still extend the analysis. You can look at the 20 GeV to 100 GeV. At this range, I will show you later the plots, the oscillation is very clean. So there is just one peak of the oscillation. So you can look at any deviation from this well-defined shape of the oscillation pattern, and then you can look again for the new physics. If you go below the 20 GeV, things get complicated because you have several oscillation peaks, and you really need a precision measurement if you want to look for something like new physics. So there are several scenarios that you can look by the atmospheric neutrinos, new physics scenarios, like the sterile neutrinos, non-standard neutrino interaction, violation of equivalence principle, extra dimensions, neutrino decoherence, neutrino decay. All of these people have done. I'm going to talk a little about the sterile neutrino, a little about the non-standard neutrino interaction, and then at the end of the talk, I'm going to tell you some stories that is happening recently in the field, that people are mixing these two together to escape some of the bounds, and I will comment on that. So, very fast, this part, because already Esteban told you. So this is the standard picture of the neutrino sector. We have three mass eigenstates. We don't know the ordering of them. It can be normal or inverted. The mixing matrix basically is a unitary 3 by 3 mixing matrix that can be parameterized by 3 mixing angles and 1 CP phase, and this will give you the oscillation in the vacuum, the oscillation probability. And you have a very good fit to the data. You can take all the data that we have from the reactor, atmospheric, accelerator, and so on. You can take all the data and fit to this picture of the 3 by 3 matrix. And these are the values that you find for all the parameters. Still there is, we don't know normal or inverted, but within each paradigm, we know exactly more or less the values of the parameters except the CP violation. But there are a few anomalies that remains. One of them is the mini-Boone LSND, which is a long-standing anomaly. Every year gets more confusing. There is this reactor anomaly. I don't think if anymore we can call it anomaly. There is this less important, I believe, anomalies that they call it the gallium anomalies, which is even less important for me, at least. But there are some anomalies that there are some hints that gives you hint on the presence of some extra states of the neutrino that should be sterile due to the Z width that Esteban told you. It should be sterile if there is another neutrino in the light mass range. So what is this extra neutrino? Phenomenologically, what you can do is that you can assume there is one more mass eigenstate, M4. What you have to do from phenomenological point of view is easy. You just extend your matrix from 3 by 3 to the 4 by 4, so you have one new column and one new row. And then you have, if you assume that this is electron volt scale, and all of these are very small, if you remember, So the difference between these, between 4 and 3, 4 and 2, and 4 and 1 is so large that you can basically assume effectively there is just one more delta m square. So you have one delta m square, and you have a few elements in your mixing matrix that you have to use them to fit these anomalies that exist. From theoretical point of view, I want to tell you that the sterile neutrino existence of the sterile neutrino is not a simple thing. It's not some perturbation to the standard model. It's really changed the field if you find some sterile neutrino in the electron volt scale. So people have to look at it, especially if you have some anomalies. It has a lot of consequences from theoretical model building point of view. All these discussions that you have about the 3 bimaximal or all the symmetries that you were assuming in the neutrino sector will change because they are based on the 3 neutrino, not 4 neutrino. Seesaw mechanism, how to implement such electron volt sterile neutrino in the theory is very complicated, basically. There are people who are working in this sense. It will change even the phenomenology. For example, the dark matter detection in the neutrino telescopes from the accumulation in the sun, you already heard about it last week, that will change. If you have a sterile neutrino in the electron volt scale, that will change because there is an MSW resonance in the sun at that if there is a sterile neutrino. And also the supernova prediction for the neutrinos will change. Even these claims that you can find the hierarchy of the neutrinos by the supernova neutrinos, if there is a sterile neutrino, it will be much more complicated because there is a possibility that you can have a wrong mass hierarchy mimicking if there is a sterile neutrino. So, yeah. Yeah.
So I think my question is, imagine that we see something. Can we actually say anything about stars or hierarchy or anything?
Well,
I mean, the supernova exploding the sun.
yeah.
That are totally fine.
Yeah.
But the oscillation pattern.
I think there are some features that are very special, like the neutronization burst. The neutronization burst is something that is impossible to avoid. If you see it, is there, it's so pronounced the peak that you cannot avoid the interpretation. And if you see it is normal hierarchy, obviously, because in the inverted hierarchy, you don't have neutronization burst. But what is happening is that if you have the sterile neutrino, you can avoid the neutronization burst, you can kill it, even in the normal hierarchy. So it gives you wrong information. You think that is normal, but it's because of the sterile neutrino. So there is this possibility that can interfere to the normal. So, and obviously, because there is a lot of far-reaching consequences of the existence of a sterile neutrino, there are several experiments. This is actually old, but I kept it because I think some of them is already, they even didn't build the experiment. So at some point, all the community, all the countries, they wanted to have one sterile neutrino search, and there were a lot of names in the field. I don't know how many of them already exist. I don't follow all these experiments, but there are several experimental activities to search for the sterile neutrino. So let's come back to this mixing matrix, 4 by 4, as I told you. When it's 4 by 4, what you need is that you need 3 new mixing angles and 2 new CP violating phases to parameterize the mixing. And I'm going to use this kind of mixing. It means that I'm going to put all the new mixing parameters before the standard one. Basically, in principle, you are free. You can mix them together, or you can put them on the other side. But using this way of parameterizing has advantage, and the advantage is that now the reactor anomaly means that theta 1,4 is different from 0. The LS and the minibune anomaly means that both of the theta 1,4 and theta 2,4 should be different from 0. And the theta 3,4 different from 0 gives you a new tau, nu S mixing, something that we still didn't probe very well. And actually, the experimental bound on this angle is very weak, I would say. Still, I think it's 20, 25 degree can be this theta 3, 4. So I'm not going to talk about the LSND mini-Boone. This is from a paper which actually Pedro Machado is one of the authors, so he will probably tell you later about the story. So the combined fit, you can see that in terms of the theta mu e, which is the mixing between the mu e, which is the appearance experiments like the LSND and mini-Boone, gives a combined fit gives you a value different from 0. So basically sine square 2 theta of this new angle is more or less 10 to minus 2 with a delta m square more or less equal to 1. And this angle, which is the effective angle, is given by the theta 1, 4 and theta 2, 4. So if this is different from 0, it means that both of them should be different from 0, and also delta m square 4, 5. And this is the latest, as far as I know, 2018, the latest global fit to the sterile neutrino. So there are groups that do this global fit just for the sterile neutrino. So, but the problem is that there are tensions. The story is not that simple. The tension basically comes from this relation between the effective mixing angles, or let's say it arises from the disappearance experiments, that they don't see any hint of the sterile neutrino. And there are limits from the meanness, from the deep core, superchemical, and Icecube, this line, that completely are in tension with the mini-Boone load region. And what I'm going to tell you, this again is from the paper of the Pedro, Icecube is included, but I'm going to tell you how the Icecube and why the Icecube is sensitive to the sterile neutrinos, how it comes. So the idea is simple. Here is Earth with the mantle and core, very simplified version. And the atmospheric neutrinos are hitting the atmosphere all the time, isotropically basically. And they produce neutrinos, and these neutrinos will propagate through the Earth. And for example, here at Icecube in the South Pole, you can see them either from the above or from the Earth crossing trajectories. What will happen is that if you have a sterile neutrino of the order of 1 electron volt square, two phenomena can happen. And these two phenomena are the MSW resonance for the neutrinos that are passing through the mantle, and a parametric resonance for the neutrinos that are passing through the core. The MSW resonance will appear. Actually, this is not also MSW, it's a constant density resonance. Is a constant density resonance appears at the 4 TeV for the delta m square 1 electron volt square. And the parametric resonance will appear at 2 TeV, again for delta m square 1 electron volt square. If you don't know what is this MSW or constant density resonance or parametric resonance, wait, step 1 will tell you. This has been proposed a long time ago, has been used in all of this paper to search for the sterile neutrino. So Icecube is collecting the data of the atmospheric neutrinos. If we see any anomaly due to these resonances, we can say that the sterile neutrino is there. Non-observation, we can put limit on the mixing and delta m square. So the impact at the end will be this, that for the theta 1, 4 different from 0, assuming that the delta m square sterile is positive. It means that the sterile state is heavier than all the active neutrinos, which is a very reasonable assumption. Otherwise, we will have a lot of problems with the cosmology. Theta 1 very different from 0 gives you a resonance in the nu E nu S, 2, 4 nu mu bar nu S bar, 3, 4 nu tau bar nu S bar. Obviously, if you have both of them different from 0, you will have both of the channels. Theta 1, 4, 3, 4, you will have both of them. Theta 2, 4, 3, 4, both of them different from 0, you will have nu mu nu S bar, nu tau bar nu S bar. And very interestingly, there is another phenomenon here, which is the nu mu bar to nu tau bar. So the existence of the sterile neutrino with both of these angles different from 0 gives you an effective mu to tau changing probability, which is easy to understand. Basically, nu mu goes to nu S, and then the nu S goes to nu tau. Effectively, will be this. So let's look at the oscillation probabilities. Here is, for example, here's the oscillation probability of the nu mu to nu mu, or nu mu bar to nu mu bar. The dashed line is the standard prediction, is a standard 3-neutrino scenario, which, as I told you, above 100 GeV, there is no oscillation. So it means that the oscillation probability is 1. And then in the presence of the sterile neutrino, you will have this resonance effect, which, for example, for the sine square theta to 4, 2 theta to 4, 4 10 to minus 2, you have this resonance in the oscillation probability at some energies, which is, this is the parametric resonance, this is the MSW resonance. At some energies, the oscillation probability is close to 0. This is very easy to see in, for the theorists. Very easy to see in the experiment because is a peak is a dip in the data. So in principle, if the Icecube has the energy distribution of the events and the zenith distribution of the events, should be able to look for such an effect. The oscillation happens just in, the resonance happens just in the anti-neutrino channel, obviously, because the delta mu square is positive. The oscillation actually depends on several parameters, not just in these two parameters, depends also on the theta 3-4, depends also on the CP violation phase theta 2-4. To make the life easier, because when you have 4 or 5 parameters, doing a fit is really difficult. So you can show that, in fact, if you want to get the most conservative limit on the sterile neutrino, you have to put theta 3-4, theta 2-4, 0. If you assume them non-zero, you will get a stronger limit. So if you want to be conservative, put them 0, and you don't need to take them into account. So you can calculate the number of events in, for example, Icecube, even IC40. This first set of the data that I showed you is easy to calculate. You have to convolute the effective area with the flux, and then do the integration on the bin. I'm not going to the detail. So here, for example, you can see the zenith angle distribution of the events integrated over the energy for some non-zero theta 2-4 divided by the theta 2-4 equal to 0, which is the standard scenario. And you can see that there is a huge deviation from what you expect in the standard scenario, which is the 1. But don't be too happy, because there are uncertainties. Basically, there are these 24% uncertainty on the normalization of the atmospheric neutrinos, which means that you are free to move it 24% up and down, this curve. And also, there is uncertainty on the tilt of the zenith distribution of the atmospheric neutrino. It means that you can rotate these curves. And you see that if I scale them up and rotate them a little, you get exactly 1. So it's not really easy to get this limit. You have to define the chi-square in such a way that take into account all of these uncertainties. And at the end, this is what we published in 2011 or 12, that we got this limit at that time on the sterile neutrino. Of course, there was no observation. But at that time, the global fit was here, so it still was escaping the limit. Of course, you can improve this limit. You have to take into account the energy distribution also. The energy resolution is important. I'm running out of time. I'm going to tell you to skip some of these slides. So you can take into account the energy distribution also. You improve the limit. It's possible to show that at the end, by binning the data over the energy, you can, by some, like 4 binning even, you can exclude the allowed region by the Minibune and LSND from the Icecube data. And this is at the end what Icecube collaboration published is official analysis, including all the details. Of course, I'm not in the Icecube. I don't have access to all the details, sensitivity. So here you can see the limit from the Icecube data, and this is the Minibune allowed region, basically excluded by the Icecube data. This was one story. I'm going to tell you a non-standard neutrino interaction now. Then at the end, I'm coming back to the sterile neutrino, because there are some claims that if you mix together, you can skip this limit. So what is non-standard neutrino interaction? Again, phenomenologically, is assuming that there are new potentials. It means that this process at the quantum field theory level, there are some non-standard contributions to this scattering. From the nu alpha to any fermion, F can be any fermion U, D electron, for example, and nu beta is another fermion. So even you can have flavor-changing non-standard neutrino interaction. So phenomenologically, what you can assume, you can add some 3 by 3 non-standard neutrino interaction. This is the epsilon, which is parametrizing the strength of the non-standard neutrino interaction. And you have to sum over all the fermions that exist in the Earth, for example, for the atmospheric neutrinos, which is U, D, and electron, to take into account all the possibilities. You can define an effective epsilon by normalizing by the number density of the down quarks. And then at the end, you will have a 3 by 3 matrix. This part is the standard oscillation. This is the effective potential, for matter potential because of the Earth for the electron neutrinos. And this is the non-standard neutrino interaction, which is a 3 by 3 matrix parameterized by these epsilons, which in principle even they can be complex numbers, but I'm going to assume that they are real. So you can do a 2 by 2 approximation. I really don't have time. Let me skip the details of the analytical calculation, how you can calculate. You can calculate the oscillation in the presence of the NSI, and at the end, in the 2 neutrino approximation, the oscillation can be given by this formula. You can see there is an effective mixing angle, an effective phase of the oscillation, which this effective mixing angle is given by this relation. R0 is the ratio of the vacuum oscillation to the NSI potential, and the R is a parameter that is changing the phase of the oscillation due to the existence of the non-standard neutrino interaction. Obviously, there is a resonance here, which is the time that the R is the minimum possible value, which is when the R0, the ratio of the vacuum oscillation to the NSI potential, is equal to the minus cosine of this value. This will be 0, so R will be the minimum value. This is really MSW, is like an extended MSW resonance in the presence of the epsilon. If you put the C0, which C is the non-standard neutrino part, you will get the usual MSW resonance for the theta 1,3. So you can calculate what happens in the resonance. Actually, what happens in the resonance is that depends on the energy. If you are in the matter-dominated part, which is in the high energy, the resonance that I told you will kill any oscillation. If you are in the low energy part, the resonance will actually give you 100% oscillation. So let's look at the plots. Here you can see the blue line is the standard oscillation of the atmospheric neutrinos, and the red line is the oscillation in the presence of the epsilon, mu tau, for example, 10 to minus 2, and epsilon prime, which is the difference between the mu mu and tau tau, is 0. So you can see that this is the resonance. Because of the resonance in the presence of the epsilon, oscillation will be 0, which means that the survival probability will be equal to 1, which in the case of the standard is actually completely different from 1. So it's a very strong effect. You can look for this effect in the data. And here you can see the oscillograms in terms of the energy and the cosine and the zenith angle. And this, in the standard oscillation, all this plot is red. Anything that is not completely red is a deviation from the standard scenario. And you can see that there are effects here that you can look at the data and search for these effects. These are in the high energy, more than 100 GeV. Less than 100 GeV, the situation is more complicated because the NSI will shift the position of the oscillation and also the height of the oscillation. So you can again plot these diagrams. Maybe this one is more easy to understand. This is the difference between the standard neutrino oscillation and the oscillation in the presence of the NSI. And anything that is blue, which means that this quantity is positive. Anything that is red or yellow, it means that this quantity is negative. So there are differences between the NSI oscillation and the standard oscillation in the low energy. There is one main point is that this is for neutrino, the other for anti-neutrino, and you can see that they are opposite sign. So if you have an experiment like Icecube, which is not distinguishing between the neutrino and anti-neutrino, you have to sum these two plots together, and basically you get 0. So you lose your sensitivity. But there is one point, and the point is that the cross-section of the neutrino and anti-neutrino are different. The initial flux of the neutrino and anti-neutrino also is different for the atmospheric neutrino. So still you get something, because it's not just adding the probabilities. You have to add the probability times the cross-section times the initial flux. And also the other point is that in the energy also the plot is changing the sign. So if you integrate over the energy, again you will get 0. So energy distribution is very important in this kind of searches. So let's go. That was for the flavor. The plot that I showed you is for the case that the epsilon mu tau is different from 0, but epsilon tau tau minus mu mu is 0. There is no difference in the diagonal elements of the epsilon. You can go to the opposite case, which the epsilon mu tau is 0, and this one is different from 0. In this case, you have the effect just in the low energy. There is no effect of the epsilon prime in the high energy. You can show it analytically. And the effect basically is, usually is weaker. So it's more difficult to look for this epsilon prime. So there are limits from the superchemical on this epsilon. You can see that in the plane of the epsilon and epsilon prime, this epsilon is epsilon mu tau. On the plane of the epsilon mu tau and epsilon prime, there are limits on the values of these two from the superchemical data. And we have done this analysis of the IC79, again, when the Icecube was not complete, what you can get the limit on the epsilon parameter and epsilon mu tau. And here, the green line is what Icecube can get, IC40, and the red line is IC79. So this was what we obtained on the limit on the epsilon and epsilon prime. Values can be written here. And at the end, the Icecube also did the analysis, and more or less the same value, the limit on the non-standard neutrino interaction. I have something like 4 minutes. Let me go to this story. There were claims recently that if you add the NSI to the sterile neutrino, you can escape the bonds on the sterile neutrino from the Icecube. First of all, new physics to the power of 2 is really the probability is 0. But if it works fine, it still is a good idea. Because you can say that there is a sterile neutrino, and then the non-standard neutrino interaction also is the 4x4 matrix. And then it's possible that in this sterile sector, we have some non-standard neutrino interaction for the sterile neutrino. Nobody measured them. Nobody still knows that they exist or no. So you are free to choose whatever you want there. And the point is that you can assume that this value is a large value, actually, epsilon SS. What happens is that you put all of them 0, and you assume a large value here, and then you diagonalize again, phase out the diagonal matrix, and then you get a large value for the epsilons. So it gives you a way to create large values for the non-standard neutrino interaction in the active sector if there is a sterile neutrino. So these authors, they proposed this scenario, and they said that if you have a sterile neutrino, so this is the oscillation probability that I showed you. The black line is the standard oscillation. The blue line is the 3+1 scenario. The red one is the 3+1 plus NSI. So you see that basically there will be no difference from the standard oscillation. This is the resonance that I told you in the 3+1 exists. But if you add the sterile neutrino NSI, the resonance will be killed. And so the Icecube bond can be relaxed, basically. So here is what they show again. So they show that this is the Icecube bond, the blue line. This is the Icecube, this is the sterile neutrino plus NSI. And you see that depending what is the value of the epsilon, you can completely make this bond non-relevant for the mini-Boole. So there is a way still to reconcile. But this is not correct, fortunately or unfortunately. I will tell you why. Again, they repeated the same thing here after 2 years. Both of the papers are PRL. Good for PRL. That you can also consider this. Limits from the meanness can be also escaped by assuming some detector NSI. These are not propagation NSI. And then also they have shown again that the Icecube bond can be from the deep core, and Icecube can be relaxed due to the existence of the NSI. But this is not correct, and I will show you why. The reason is that they just considered this part of the data after 500 GeV above. So the green line and the violet one is the data that they analyze in that papers, and they show that the bond can be relaxed. Here, I'm showing the full range of the energy, and you can see, for example, this is for the neutrino, there is no resonance in the neutrino, and this is for the anti-neutrino. So the red one is the 3+1 that you had this resonance here, but when you go to the blue line, which is the NSI plus 3+1, here there is no resonance peak, but here there is a resonance peak. And the resonance peak exactly is in the gap of the energy analysis that they are doing. So they are missing this gap just because of some cuts on the energy analysis, not a physical one. The same thing is for the other also cosine C. You can see that the 3+1 goes there. Analytically, it's very simple to understand because the resonance energy has such a relation in the 3+1 plus NSI has such a relation with the NSI values. So by changing the NSI values, what happens is that you can change the position of the resonance, but not killing it. Actually, there are some points that you can kill it, but this is not what they propose. And also for the other ones, you can see, for example, this case, you can see that here the 3+1 is you have a resonance in the TeV range. If you add the NSI, the blue line, there is no resonance in this range, but there is a huge difference in the middle due to the presence of the sterile neutrino and NSI together. So we have done the analysis and we have shown that in fact, if you take the NSI also into account, plus sterile neutrino, the bonds will be much more strong, not relaxed at all. So there is no way for the moment to escape from the bonds from the Icecube. And I believe that is one of the most important pieces of information in the sterile analysis. Pedro can tell you later, because this is one of the ways, this is the only data set that you have that is actually is not oscillation. It's a resonance effect. And that is very important, because you don't have oscillation, it's a resonance effect. And that is very difficult to avoid, generally. So I had some other things to show you about the cascade, but I'm already finished, I think, the time. So I'm going to stop here. And then my final message will be that the sterile neutrinos are in big problems. There are other solutions probably to the problem. I think Pedro will tell you some other ways to think about how it's possible to solve the mini-Boone anomaly. Maybe at the end, as Esteban said, it's just an experimental problem. It's not a theoretical problem, but who knows. The Icecube can put a strong limit on the sterile neutrinos through the resonance, and also at the same time on the NSI, and adding the NSI will not solve the problem to the sterile neutrino. Thank you.
Questions?
So, did the experimentalists analyze that gap in the data,